Namaste, good evening. Welcome to Lecture 7 of NPTEL tutorial session of Thermodynamics course. So today we will be discussing week 6 assignment and week 6 revision questions. These are based on Carnot cycle. So Carnot cycle, so general remarks I'll be saying. So it is as follows. So Carnot cycle. Um, So it is consisting of 4 reversible processes. So first one is isothermal heat addition. Then second one is adiabatic expansion, adiabatic or isentropic as we say. So this isothermal heat addition will take it to TH, then expansion take it from TH to TL. Then third one is isothermal heat rejection. So it will be reaching the low temperature TL, and then again adiabatic compression. Okay, one second. Okay, adiabatic compression, which is happening from TL to TH again. Okay, so now some key formulae of Carnot cycle. Sorry. For Carnot heat engine. First is thermal efficiency. Which is eta Carnot equals 1 minus TL by TH. Now, heat transfers in Carnot engine can be represented as QH by TH equal to QL by TL, and work can be calculated as QH minus QL. Okay. Now for Carnot refrigerator, or Carnot heat pump, coefficient of performance equals T cold by T hot minus T cold. And this is for refrigerator, and COP for heat pump equals T hot by T hot minus T cold. Then for isothermal steps, again heat transfer can be expressed as Q hot by T hot equals Q cold by T cold. Now we'll go to revision questions. So the first one, a person states the following processes for a Carnot cycle. It has two adiabatic processes and two isobaric processes. Is this statement correct? So the statement is incorrect. Sorry, incorrect. Why? Because Carnot cycle has got two isothermal processes, not isobaric. So it is isothermal. Okay. So adiabatic is there, or isentropic processes are there, and then two isothermal processes are there. So there is no constant pressure process in ideal Carnot cycle. Now, second one, a refrigerator receives 100 watt from a reservoir at 260 Kelvin and transfers it to a reservoir at 310 Kelvin. What is the minimum power that is needed to accomplish this process? Okay, so for a Carnot refrigerator, we have seen the COP equation, right? So this one is for coefficient of performance. We can calculate um, COP for a refrigerator using the equation T cold by T hot minus T cold. So using that, we can find COP. Then we know that, okay, minimum work equal to Q cold by COP. So Q cold is given 100 watt, right? Because it is the heat received um, at a lower temperature. So Q cold by TL. Okay. So from there, that Q cold we have got and COP we have calculated. Using that, you can find the W minimum. Now the third question. Should the heat transfer process in Carnot cycle be externally reversible? So the answer is yes. Why? Because a process is externally reversible if there is no entropy generated due to this temperature gradients. So in a Carnot cycle, it is isothermal heat transfer that is happening. So there is only this infinitesimal temperature difference between the working fluid and the reservoir. So that ensures reversibility. Okay. Then fourth question, which processes of a Carnot cycle are possible to realize, at least with restrictions? So adiabatic processes, if you are using good insulation or if you are taking like a limiting heat transfer with by conducting them quickly, then that is like realizable. Isothermal processes, it can only be approximated, like a if you're taking a quasi-static heat exchange with a very large reservoir. So large reservoir ensures that the temperature will be uniform in that reservoir. So only then you can say that isothermal processes can be realized. So both we have to approximate. So one is like adiabatic. If you want to realize it in real life situation, then you have to use insulation and all. And for isothermal, you have to use a large reservoir, and the process should be quasi-static or very slow process. Okay, next is which process? Okay, fifth question. The peak temperature in a coal-fired power plant is about 1000 degrees centigrade, and the condenser dumps heat into the ocean water that are at 23 degrees centigrade. What would be the maximum possible efficiency of this thermal power plant? Okay, so first what we have to do is convert everything to Kelvin. Okay, then find eta max equal to 1 minus TL by TH. Using that equation, you can find eta max. So that will give you the maximum possible efficiency, okay, of this thermal power plant. Yeah, so that will come around 75 because it's like 1000 is 1273, and 23 is like 300. So it will give you almost like 1 by 4. And 1 minus 1 by 4 will be almost like 75 percentage. Okay, 0.75, that is 75 percentage. Now, sixth question. A person says, on a pH diagram, the Carnot cycle is rectangle. Is this correct? So a Carnot cycle is typically shown as a rectangle in TS space, not P. So TS, if you say, uh, that is where it will be rectangle. Okay. So it is rectangle in TS space. So the isotherms will be horizontal lines. Isothermal processes are horizontal lines, and the adiabatic processes will be vertical lines at constant S. Right. So it will be like this. So T will be there, two temperatures, TH and TL. So what will happen? It will be two horizontal lines. So okay, two horizontal lines, and then S will be there. So S1 and S2. So it will be isentropic processes will be two vertical lines. Okay, so that will be the rectangle diagram, not pH diagram. Do you agree with the statement that heat engine efficiency cannot be 100%? Um, okay, so yes. Why? Because TL is always greater than 0. Right. So by this Kelvin Planck statement of second law, no cyclic device can convert all heat from a single reservoir into work. So it must always reject some heat into a heat sink or a lower temperature reservoir. So that means TL is always greater than 0. So 1 minus TL by TH, TL will be always some positive value. So it is going to take, so there will be something to reduce or deduct from that one or the maximum efficiency. So that will be very, you can always try to reach 100%, but 100% efficiency is quite impossible because of second law constraints. Next question. An engineer says that if for a cycle the cyclic integral of delta Q by T is 0, then it has to be Carnot cycle. Do you think that it is correct? So my answer would be not necessarily. Why? Because see, this integral delta Q by T equal to 0. This is what they were saying. That is for a uh, reversible process. Okay. So we can have any kind of fully reversible cycle that exchanges heat at more than 2 temperature. But a cycle with exactly 2 heat exchange temperature is indeed a Carnot cycle. But a general reversible cycle might have a different shape, right? So this this delta Q by T only ensures that this is a reversible process happening with the heat exchange happening. It can this delta Q by delta T, sorry, delta Q by T integral delta Q by T equal to 0 is a reversible process or reversible cyclic process. So in that cycle there can be multiple heat exchange that can happen. It is not saying that only exactly 2 is happening, right? So if it is only 2 is happening, then again it can be Carnot cycle. But if it is like multiple heat exchanges are happening, then it is not Carnot cycle. So it is having a different shape of that cycle diagram. So this is not completely correct. Now, ninth question. A refrigerator engineer is asked the following question. I want to transfer 500 watt of heat from a room at 25 degrees centigrade to the ambient air whose temperature varies daily between 27 and 45 degree. For which condition should I design the compressor and its motor so that its power consumption is the smallest possible? Okay, so COP is like uh, okay. So when we are talking about power will be um power will be less. I mean, power required will be less if there is only small temperature difference. Okay, so delta T is less. So we have to design it for the smallest um, temperature, outside temperature. So if you're taking delta T is smaller, then COP will be higher. Okay, so that is how we have to design. So we have to take the lowest temperature, outside temperature. So T hot should be lower. Now, next question. Uh, in the previous problem, for a given refrigeration cycle, will it consume the minimum amount of power at every outside temperature? So for the same refrigeration cycle, if the outside temperature rises, then COP goes down, right? So that means bigger denominator. Delta T will be higher, so bigger denominator means the whole value of COP is smaller. So COP goes down means more power consumption will be there. So it will not stay at that same minimal power condition. Okay. COP down, power consumption high. That means T hot high. T hot high means COP low. COP low means power consumption is high. Okay. Now, 11th question. In a cold climate, the outside temperature um, varies between minus 25 degree and 5 degree during certain months of the year. A limited amount of electricity is available for keeping the inside air of a tent warm. Two options are available. First, use an electric heat convector, or second, use a window air conditioner as a heat pump. For the same power consumption, which device will supply more heat to the tent inside air? Okay, so they are talking about using a window AC as a heat pump. Okay, so window AC as heat pump means what? Uh, so a heat pump can have COP greater than 1, right? So it delivers more heat to the inside than the electric power it consumes. So like the work that we are giving, uh, than that it can provide heat to the inside of that room. So the difference is taken from where? From the cold ambient. So now an electric resistance heater should have at least 1 COP. So the heat pump is more effective in delivering heat per kilowatt of electricity. So it will be having more efficiency when compared to electric heater. Okay. So heat pump. Heat pump is the answer. Because COP is greater than 1. Now, next question. Under steady operating conditions, an electric motor consumes 25 kilowatt power from a three-phase 440 watt volt power supply. It delivers a certain amount of shaft work, product of torque and speed, is the ratio of output power to input power governed by Carnot cycle efficiency. Okay, so they are talking about a motor converting electrical energy to mechanical work. So second law limitation uh, for a Carnot engine is not applicable for a electric motor. The second law limitations are there, that is not applicable. So motor efficiency is going to depend on electrical losses or friction or magnetic losses, etc. Okay, so the answer is no. Second law limits only heat engines. 13. A power plant is designed for a location that is north of 60-degree latitude. The manufacturer of the power plant gets an order for setting up the same power plant at a location that are located between 15-degree north-south latitude. Will the thermal efficiencies of the power plant be the same at both locations? So, probably not. Why? Because the ambient conditions differ. Okay, like 15-degree latitude and 60-degree latitude, one is like near North Pole, another is near equator. So equator, we know that it is slightly hotter. So the ambient conditions will be hotter, and 60-degree latitude means the ambient condition will be really cold. So that affects the sink temperature, thus the overall efficiencies. So no. Okay, that is the answer. Because ambient temperature different. Okay. Now, 14th question. An air conditioner operates in ambient temperature of 25 degrees centigrade while keeping a room temperature of 22 degrees centigrade. The same equipment is shifted to a location where the ambient temperature is 35 degrees centigrade. Will there be any change in its power consumption? Okay. So, power consumption will increase because the temperature has shifted. From 35 to 22 is bigger. So the system COP is going to be lower. Why? Because the delta T is higher, right? So more power is drawn from the for the same cooling. Okay. So the answer is it increases because COP decreased. Okay. It means power increases. Okay. Now, does a thermoelectric refrigerator violate the second law of thermodynamics? Thermoelectric refrigerator. So that is thermoelectric means Peltier. That is the device name. Okay. So Peltier devices follow the same laws. So they require external electricity and do not produce 100% efficiency or anything unphysical. But they have a lower COP lower than a vapor compression system, but it does not violate thermodynamics. Okay, so no is the answer. Okay. Now, 16th question. A Carnot cycle heat engine operates between a source at 1000 Kelvin and sink at 400 Kelvin. If power output is 600 watt, uh, then which of the following statements is or are not true? So cycle efficiency will be 60%. Heat transfer rate from source will be 1000 watt. Heat rejection rate to sink will be 400 watt. Heat rejection rate to sink will be 1000 watt. And these are the question. So Carnot engine between 1000 Kelvin and 400 Kelvin has power output 600. Okay, so first we have to find efficiency. Efficiency equal to 1 minus 400 by 1000 TL by TH equals 60%. So that's right. Now, if W equal to 600 watt and eta equal to 60 or 60%, then QH equal to W by eta equal to 1000 watt and QL equal to QH minus W equal to 400 watt. So B and C both are true. Okay. Now, 17th question. Prove that a cycle that violates the Kelvin-Planck statement of the second law also implies violation of the closure statement of the second law. We have done this question before. So Kelvin-Planck violation means the inverse of Kelvin-Planck statement will be what? You can extract work from a single reservoir with no other effect. Okay. So if you combine that device with a reversed heat engine, for example, a heat pump or a refrigerator, you can transfer heat from cold to hot. Okay. So transferring heat from cold to hot without net work input violates closures. Okay. So violation of one implies the violation of other. Okay. So what is the thing? Kelvin-Planck statement, KP statement says extracting work from single reservoir with no other effect. Okay. So violation of KP statement. Violation of KP statement implies this thing. Okay. No other effect. Now, that implies what? That implies you can combine the device with a reverse heat engine and then you can transfer. So if you combine the device with a heat pump, then heat transfer from cold to hot without network done will happen. So that implies it violates Closius statement 2. Okay. Now, next question. Which of the following statement is not true for the Carnot cycle heat engine? So the process goes from 1, 2, 3, and 4, and then back to 1 again. So this is in TS diagram. So they have given some options. So we will discuss one by one. Okay. So pressure decreases for a part of the heating process. Then in 3 to 4 process, wet steam is compressed. Then the condensation process is not isothermal. Fourth option is there is no wet state in the turbine. So for a Carnot cycle with a phase change fluid, both evaporation and condensation occur isothermally. Okay, if they are saturated process. So the statement the condensation process is not isothermal is false. Okay, so that is the only thing which is not there, because you can see this wet state is there because the cycle exists between the inside the dome area, right? So there is a liquid vapor mix is there. 3 to 4, what is happening is wet steam is compressed. That's why the temperature is going from TL to TH. And pressure decrease for a part of the heating process is expansion is happening. So pressure decrease is happening. So that is how it is. Only C is wrong. Okay. Evaporation. I'll write it over here. Evaporation and condensation happens at at constant temperature or isothermally. I can write isothermally. Now, next question, 19. So which of the given TS cycles cannot be Carnot cycle? So Carnot cycle in TS diagram, the Carnot cycle must have two horizontal lines, which are the isotherms, and two vertical lines, which are adiabatics. So any diagram that is not showing a perfect rectangle in TS phase is not Carnot cycle. So the option will be C. Okay, so C is the wrong answer. Now 20 is a business owner. Okay, to curb CO2 emissions from his power plants, the business owner, qualification BBA, MBA, okay, fine, says to his engineers, you guys can get only 45% efficiency. Get me 80% efficiency, else you're fired. What would you do next? Yeah. So by second law, if your hot and cold reservoirs correspond to, say, a typical steam power plant, so steam power plants will be having around 600 degree, 700 degrees centigrade for boiler, and ambient temperature condenser. That is like room temperature. If you're taking 25 degrees, that will be the condenser temperature. So maximum theoretical efficiency is around like so 60 and 30. If you're taking, it is around 60%. So achieving 80%, you can forget about it. It is not possible at all. So correct response is that it's not our fault. It is the second law who has to be blamed. Okay, so second law prevents such a high efficiency at the reservoir temperature. Okay, or if he's pushing you again, you have to resign and run. Okay, that is what you can do. Okay, so you will explain. You will try to explain that due to um, reservoir second law, the efficiency is limited by the reservoir maximum efficiency. Okay, max reservoir temperatures like TL and TH. So without this, you cannot do anything about it. So 80% is efficiency and all in a real life scenario is not possible. Now assignment questions. So we have got 7 questions. The first question is, a Carnot heat engine receives 800 megajoule of heat from a source of unknown temperature and rejects 350 megajoule to a sink at 24 degrees centigrade. Determine thermal efficiency of the heat engine, minimum temperature of the source for the cycle to be possible, maximum temperature of the source for the cycle to be possible. Nice. So they have given what all. So one is it is receiving heat. QH is given. This is QL. Okay. Now work done, we can find work done equal to QH minus QL. You can find it like 800 minus 350 is 400. Sorry, 450 megajoule. Then, so thermal efficiency is what? W by QH equal to 450 by 800 equal to almost like 0.56. Okay. And then, yeah, 25. Okay. So 56 percentage approximately. Okay. Now, now for temperatures, you have to check this one. QH by TH equal to QL by TL. So TL equal to, so this TL is given as 24. So TH equal to 800 by 350 times 24 to 273 equal to 297. So approximately 600 something will be coming. You can check that. In Kelvin we will be getting, okay, TH in Kelvin. Okay. So what does this value represent? So the thing is, Carnot cycle, we know that it operates between two temperatures. One is low and one is high, because it's both are at different temperatures. So one should be like, when you compare, one should be high, one should be low. Now at one temperature, it is absorbing this high heat value, that is 800 megajoule. So that is that is from the source, and it is rejecting 350 megajoule again isothermally at constant temperature of this 24 degrees centigrade to to a lower or heat sink. So then what they are saying is, if this should be happening, if this should be possible, or this is possible only when this isothermal uh, you know heat addition, or sorry, isothermal temperature of this receiving heat at 800 megajoule should be this TH value. Only then this process will take place. Otherwise, if it should reject this heat of 350 megajoule at 24 degrees centigrade, and receive 800 megajoule, then that receiving of 800 megajoule should be at this value of TH. Only then this process will be possible. So the minimum and maximum temperature is this two temperatures in an ideal scenario, where the cycle must operate isothermally at the reservoir's temperature. So the lowest feasible is this TH value of uh, whatever we have calculated. So that should be the minimum value. Okay. Mm. Now, next is second question. Which of the following cycles can attain Carnot cycle efficiency? Give reason. Again, this is TS diagram, so it should be rectangle. So two horizontal lines, two vertical lines. So any deviations from that shows it is not an ideal Carnot cycle. So um, only B is correct. Okay, rest of everything has got some kind of a deviation, so that is not possible. Now, third question. The maximum attainable temperature of the combustion products from a combustion reaction is called the adiabatic flame temperature. More in week 11 of the course. Okay. Okay, about adiabatic flame temperature, they will be teaching later. So with a hydrocarbon as a fuel that burns in air, the adiabatic flame temperature is approximately 2400 Kelvin. The lowest temperature on Earth at any instant is about minus 40 degrees centigrade. What is the maximum possible efficiency of a Carnot cycle heat engine operating between these two temperatures. Where could such a power plant be located, and what practical issues would it face? Okay, very nice question. So maximum possible efficiency we can find from TL and TH, right? So TL is what? TL is around uh, minus 40 degrees, 273 minus 40 it is 233 Kelvin, and TH is they're saying 2400 Kelvin, right? So eta equal to 1 minus 233 by 2400 equal to almost like 90%, because take it as 240 above. Okay, 240 by, so 1 by 10, 1 minus 1 by 10 is almost like 90. Okay, so 90 percentage. Now this extremely cold sink will be in some places like Siberia or something. Okay, very, I mean, North Poles or Siberia, uh, such cold deserts are there in our world. So that will be this place where this extremely cold conditions will be possible. Even then, this very extreme temperature won't be always stable. That is one thing. So it will increase with weather change that is happening. Another thing is this hot material, like the temperature of 2400 Kelvin and all, the material cannot withstand such a temperature. Like it will create mechanical failure at such a large temperature most of the time. And cold enough sink temperature also, so that kind of a thermal gradient, if it is there, then mechanical, the material is prone to mechanical um, failure. So that is a very difficult situation because of thermal expansion and all those things. So and this real system is going to have a lot of irreversibility. So this is about the theoretical maximum efficiency. We are talking about 90 percentage, but in reality efficiency will be much lower because of this kind of irreversibilities that will take place in this system. Now fourth question, in a hot region a building has to be air conditioned using electricity from SPV panels, solar photovoltaic panels. Okay. Uh, Inside temperature is to be maintained at a steady 26 degrees centigrade, and the outside design condition is to be taken as 50 degrees centigrade. The cooling rate is to be 10 kilowatt. Now calculate minimum power required for running the air condition and its COP. How much energy is required to drive the air conditioner for 12 hours? SPV say, okay. We will see one by one. So first is minimum power and COP, and they have given T hot and T cold. So this is T hot and T cold. We have to take it in Kelvin. So T cold is what? T cold, TCL, right? TC is 299 Kelvin and TH is 323 Kelvin. Okay, that is found. Now COP equals to T cold by T hot minus 3. T cold equals to 299 by 24. Okay, almost like 13. Okay, approximately 13 it will be coming. COP. Now cooling load they have given us 10 kilowatt. Okay, that is the cooling load or Q cold. Okay, now W minimum will be Q cold by COP equal to 10 by 13, almost like 0.8 it will be coming. Okay, now next question is energy in 12 hours they are asking. So 12 into 12 times 0.8 kilowatt that we have to find. Then next is SPV. So they are saying, one second. Okay. Okay. Next question is SPV. Okay, about SPV they are saying. So average solar flex is 400 watt per meter square, and it is effectively receiving this kind of a solar flex for 8 hours. So calculate the area of SPV and the storage battery capacity. Okay, so first we need, this is the total energy that is required. Total energy required equals to this one. So 8 12s are 96, so 9.6 uh, kilowatt. Kilowatt is the total energy requirement. So kilowatt hour, time is in hour, right? So kilowatt hour is the total power requirement. Okay, sorry, energy requirement. So this now we need this 9.6 kilowatt hour, and SPV is only active for 8 hours, and it is receiving like 400 watt per meter square of uh, solar flex. So in 8 hour, 1 meter square will yield how much? So in 8 hour, 1 meter square will yield 0.4 kilowatt times 8 equals to 3.2 kilowatt hour. Okay, so total is what? 9.6 kilowatt hour. So area equals 9.6 divided by 3.2. That is almost like 3 meter square. Okay. So battery capacity should be like 9.6 kilowatt hour to power the AC for the requirement of 12 hour. Okay. And this SPV should be having an area of 3 meter square if it is like receiving this solar flex of 400 watt uh, watt per meter square for 8 hours. Now, instead of the SPV, the electricity were to be generated from a Carnot heat engine operating between reservoirs 1500 degrees centigrade and 50 degrees centigrade. What will be the heat supply rate from the reservoir and the engine efficiency? Okay, now temperatures are given TH and TL. TH equal to 1500 plus 273 is 1773 Kelvin, and TL equal to 50 degree, that is 273 plus 50 is 323 Kelvin. Now eta we can find, it 1 minus TL by TH equals to almost like 1 minus 323 by 173. So 1 minus 2 by 10. 2 by 10 is 0.2, 1 minus 0.2, 0.8. It will be coming approximately. So that value, if you take, then use it for QH calculation. So W by eta. So air conditioner needs how much? 0.8 kilowatt hour, right? That is what we have found. So minimum value for minimum power required is how much? It's 0.8 kilowatt. So that 0.8 kilowatt we will be taking 0.8 by 0.8. It's almost like 1 kilowatt should be the QH value. This is how we will be finding. Now, next question. Which of the following statement is not true for the Carnot cycle shown below? The pressure decreases for a part of the heating process. In the 3 to 4 process, wet steam is compressed. The condensation process is not isothermal. There is no wet state in the turbine. Okay, so answer is like Carnot cycle. What is happening? Like evaporation and condensation. That is heat addition and heat rejection are both isothermal if they are happening at saturation. So condensation process is not isothermal is incorrect. Okay. So C is incorrect. We have discussed this in assignment, revision question also. It's a repetition of question. Now, sixth question. A refrigeration operates on the Carnot cycle shown below in a cylinder piston arrangement with helium as working substance. Calculate the COP, specific work, specific heat transfer, and specific entropy change in each process for the following condition. So T3 they have given us 100 Kelvin and S3. Okay, I'll just mark it over here. T3 P I think something is wrong. They have marked it in the wrong way, I guess. It should be like 1, 2, 3, 4. It should be 4 should be coming here or here. Okay. S3 is greater than S2. So actually the marking should be in some other order. So I'll be marking it again. So we'll take 1, 2. Sorry. Okay, this is how it should be. So here they are saying temperatures they are giving. T3 is 100 Kelvin and T4 is 140 Kelvin and S3 is 1.5 kilojoule per kilogram Kelvin, and here it is. Sorry, my bad. So S3 and S2 they are correct. Okay, S3 is 1.5 kilojoule per kilogram Kelvin, and S2, so it should be coming like the other way around. So 3 is fine, 4 should be here, 1 and 2. Okay, this is how it should be. So 2 is 2.5 kilojoule per kilogram Kelvin and P4 is 140 Kelvin. Okay, this is how the temperature should be marked. Should be the other way around. 1, 2, 3, 4. Then only this values can be, because T3 and T4 are at two different temperatures and S3 and S2 are at different adiabatic processes. So this should be how it should be marked. Okay. So they are saying to compute a COP, we know like temperature ranges are given, so we can compute it directly using uh, the equation. Then specific work, specific heat transfer, specific entropy change, delta S, and everything is given. So it is a direct question. Uh, so COP, you just use TC by TH minus TC. Then specific heat transfer, use so isothermal absorption is happening. So T cold is 100 Kelvin. So Q cold, QC equals to uh, TC delta S. So delta S is 1 and T cold is 100 Kelvin. So it is almost like 100 kilojoule per kilogram. Then specific heat transfer, specific work is asked. Q hot is found. Sorry, Q cold is found. Now Q hot is TH delta S. So TH is 140. That is 140 kilojoule per kilogram. So work equal to Q hot minus Q cold. And specific entropy is delta S. So that is 1 kilojoule per kilogram Kelvin. So that's about it. It's all direct equation we can use. Now, seventh question. Which of the following statement is not true for the Carnot cycle shown below? The pressure increases during process 2 to 3 and 3 to 4 and decreases during process 4 to 1 and 1 to 2. The working substance is always an ideal gas. The cycle has work output during process 1 to 2 only. There is no heat transfer during process 3 to 4 and 1 to 2. Okay, so Carnot cycle does not require the working fluid to be ideal gas. It can be steam or vapor or even real gas. So B is not always true, not true. Okay. Now, typically in heat engine, uh, both expansion uh, produces work, not just one process. So if C says that only work output only occurs in 1 to 2, that is not always true. Okay, so not true or false. Now, for a Carnot cycle, two adiabatic processes have no heat transfer. That is why it is called adiabatic. And two isothermal processes will be having heat transfer. So, because heat addition or heat is being taken away at isothermal or at a constant temperature. So, if diagram is saying that okay, from 3 to 4 and 1 to 2 are adiabatic, uh, then uh, then the order, so there is no heat transfer during process 3 to 4 and 1 to 2. Um, that is correct. Okay, that is correct. Now, pressure increases during process 2 to 3 and 3 to 4 and decreases during process 4 to 1 and 1 to 2. 4 to 1, what is happening? Expansion is happening. Expansion. So, yes, and this is compression is happening. Okay, that is also true. Pressure increases from 2 to 3 and 3 to 4 and decreases during 4 to 1 and 1 to 2. Yes, that's correct. So that's about the problem solving session of week 6. I hope it was a useful tutorial. Thank you for attending.